That is for use later and will be made available on herox.com. Please keep your microphones on mute. We've all been on Zooms for the past 2 years, so everything else should be pretty straightforward. If you have a question, submit it into the chat box. We will be keeping an eye on that. And questions, technical questions from GTO can be answered, as well as questions directly from the teams themselves. If you have any technical issues related to Zoom, I am the technical support, so you can direct message Lindsay or send me an email, lindsay.mcgurk@nrel.gov. Also, the first thing to do is also make sure that you check your audio tab. That's usually the source of any issues. Prize related and technical questions after today can be emailed to our Geo Lithium extraction at nrel.gov email box. First and foremost, we want to thank our IAP members. Thank you for all the support throughout the entire prize process and for your support during today and Thursday's pitch sessions. Our pitches today will follow the same format for each of the 15 teams. We'll have a 5-minute pitch. So each that's backwards. Backwards. We have 10-minute pitches. So everybody, don't worry, your pitches are 10 minutes. And then the Q&A will be 5 minutes for each team. And we will hear from 8 semifinalists during today's session. And there is a second session on Thursday where we will hear from the other 7 teams. With that, I would like to introduce Sue Ham from the Department of Energy's Geothermal Technologies Office.
Hi, everyone. I'm so excited to be here. Thank you for having me as part of this pitch session. I just wanted to sort of set the stage and talk a little bit about why we in GTO are doing this, why this is so exciting, that kind of thing. I know I'm sort of preaching to the choir here, so just bear with me. Okay, so the first thing is to understand, right, why critical materials are so important to the Biden administration. And in February of 21, the president signed Executive Order 140117, which was America's supply chains. And that states in there, it says, the United States needs resilient, diverse, and secure supply chains to ensure our economic prosperity and national security of our critical mineral and material supply chains. Resilient American supply chains of critical materials will revitalize and rebuild domestic manufacturing capacity, maintain America's competitive edge in research and development, and create well-paying jobs. In February of 22, the administration continues to announce major investments in domestic production of key critical minerals and materials, ensuring these resources benefit the community and creating good-paying union jobs in sustainable production. To address the critical materials supply chains, the administration is encouraging production of critical minerals and materials, all with a laser focus on boosting strong labor, environmental and energy justice, community engagement, and tribal consultation standards. Great, that's sort of at the administration level. But the Geothermal Technologies Office is part of the Office of Energy Efficiency and Renewable Energy. And so how does critical minerals fit into all of that? And the prize, so the Office of Energy Efficiency and Renewable Energy has a number of priorities. And I'm just gonna talk about a few of them and how critical materials feeds into each of those. So the prize that we are all here for supports decarbonizing the electricity sector through the co-production of geothermal energy production and lithium extraction, right? If we can extract lithium from geothermal brines, that is going to make geothermal energy that much less expensive, that much more economically feasible. It supports decarbonizing the current lithium transportation supply chain for battery materials by securing a domestic and clean source of supply of lithium. And then, of course, we want to decarbonize the current lithium industry. Lithium extraction has null amounts of CO2 emissions, minimal water use, and significantly smaller footprint as compared to hard rock mining or evaporative pond extraction methods. And then lastly, I want to just talk for a moment about how the work fits into the new Geothermal Technology Office multi-year program plan. The significant increases in market demand for critical materials such as lithium, combined with the low number of US resources currently available for sourcing these materials, underscores the strategic importance for the United States to identify new upstream critical materials resources and to advance economically competitive critical and strategic material extraction from resources such as geothermal brines. California's Salton Sea represents an outsized opportunity, as we all know, to diversify the domestic supply chain of materials, particularly lithium, with an estimate of 600,000 tons per year of lithium carbonate. And among that last bit, I just want to mention one of the things that GTO, in addition to this prize, is also doing is we have recently awarded Lawrence Berkeley National Laboratory a $1.2 million award to quantify the sources and amounts of lithium present in geothermal brines within the Salton Sea area by, number one, developing a better constrained geologic model of the reservoir, two, understanding what is controlling the concentrations of lithium, and three, looking at how the lithium concentration may decrease over time. The project is also going to look to quantify the fresh water and chemical usage, as well as air quality during the lithium extraction process. So I just wanted to give you, with just a few minutes up front, is an idea of how we see this prize fitting into all of these different levels of priorities. As you can see, it's critically important across all of them. And so for that reason, we are super excited to be here for this pitch session, and on Thursday as well. With that, I'll turn it back to you. Lindsay, are you taking over? Alex is. Thanks, yes, everybody.
Thank you, Sue. And yes, we'll turn it over to Alex.
All right. Thanks, everyone. Thank you, Sue, so much for opening our sessions for today and underlining how important, again, the work that you're doing for this prize is not only for DOE, but the Salton Sea across the board. So if you don't know me, hi, everyone. I'm Alex Priestachef. I'm also with the Department of Energy Geothermal Technologies Office, and I am the Geothermal Lithium Extraction Prize Lead. Again, I want to welcome everyone also to today's innovation pitches. And I also want to give a special shout out to all of our industry advisory panel who are on the call, and they'll be providing our 15 semifinalist feedback on their presentations to consider as we're quickly approaching the phase 2 submission deadline. So now with that, I'll go ahead and turn it back to you, Lindsay, for some housekeeping, if there's anything else we need to cover, or go ahead and get started.
Yeah, sounds good. Just a reminder for everybody who has joined since the beginning, we will be doing 10-minute pitch sessions with 5-minute Q&A sessions. And we will get that started now, starting with Team Teleport from the University of Virginia.
All right, should we just go ahead and start, or should
All right, Jeff, yep. You will start your time when you're ready.
And I'll just ask you to advance slides as we go.
Exactly.
All right, sounds great. Well, good afternoon. I'm Jeff Geis, team lead of Team Teleport, or the Targeted Extraction of Lithium with Electroactive Particles for Recovery Technology team. Next slide, please. Team Teleport is developing technology at the University of Virginia in conjunction with industrial partners at Power Tech Water. Team Teleport brings together experts at the University of Virginia in the areas of selective membrane transport, intercalation materials, electrochemistry, and metal organic framework materials. We've partnered with Power Tech Water because of their expertise in electrochemical wastewater treatment, electrochemical metal recovery, and their expertise in commercialization. Next slide, please. This partnership is developing a technology for recovering lithium from geothermal brines that is based initially on capture of lithium in an inorganic intercalation material. Our inorganic crystalline intercalation material is redox active and can be reduced to drive lithium capture from the complex brine solution. The crystal structure of our intercalation material is highly selective for lithium, meaning that the vast majority of the complex and aggressive brine contaminants will be excluded from the intercalation material structure. Intercalation of lithium into the material can be driven by the redox potential of the brine itself, or abundant and inexpensive redox shuttles can be used to cycle the intercalation material between the lithium capture and release modes. The net result of this capture and release process will be a concentrated lithium solution leaving the intercalation material packed bed, far simplified from the geothermal brine feed. The brine components not intercalated into the packed bed material can then be re-injected into the well. Following the intercalation material packed bed, the simplified and concentrated lithium solution will pass to an electrolysis cell where the lithium hydroxide monohydrate product will be isolated. This approach has the added advantage of providing an opportunity to oxidize the redox active material or shuttle at the anode such that it could be recycled to drive lithium release once again from the intercalation material. All of this means that we can operate a closed loop system to capture, release, and purify lithium via this intercalation material and electrolysis system. Following electrolysis, the lithium hydroxide monohydrate product can be further purified using additional membrane or sorbent-based technologies. Next slide, please. A significant advantage of the team teleport approach is lithium capture and concentration via an intercalation-based process. This step decouples the initial capture of lithium from subsequent processing and protects the more sensitive lithium separation processes from the very complex and aggressive brine solution. Our approach can be driven by redox active compounds in the brine itself, or by abundant and inexpensive redox shuttle compounds that can be used as part of a closed loop system to further minimize the impact of those materials on the process. Our technology is scalable and space efficient, and it simplifies downstream purification because the complexity of the solution is substantially reduced after the intercalation material step of the process. Following the lithium capture and release step, our product is isolated and purified using metal organic framework-based materials. Next slide, please. In phase one, we set out to tackle two project goal areas, one focused on the intercalation material and the other focused on the MOF-based selective membranes and adsorbent materials for the enrichment and final purification of the lithium hydroxide monohydrate product. Key goals for the intercalation material are high usage of the intercalation particles, selective capture of lithium and perhaps other monovalent ions such as sodium or potassium, but not significant amounts of multivalent ions. And finally, high lithium recovery. Key goals for the MOF material are mechanical, thermal, and pH stability, as well as favorable lithium selectivity relative to the other monovalent ions that may intercalate along with lithium in the initial part of our process. Next slide, please. Ion capture and release from our intercalation material can be tracked and independently verified using open circuit voltage bench scale measurements, such as those seen here in this photo from the laboratory. This capability is due to the redox potentials associated with the different states of the material, and several candidate redox agents or shuttles can be used to convert the intercalation material to drive lithium capture or release. Some of these compounds are found in the native brine itself, and others are abundant and inexpensive compounds that could be incorporated into the process. In many cases, the compounds could be oxidized in the anode of our electrolysis cell, rendering them ready for recirculation to the packed bed as part of a closed loop process. Next slide, please. Our metal organic framework-based lithium selective materials leverage technology that is known to be selective for lithium over other ions. These metal organic frameworks have a long history of enabling molecularly specific separations, and in particular, separation of lithium. We are preparing and characterizing metal organic framework-based membranes and adsorbent materials in our laboratory, and we're using a newly developed method for making what we call polymorphs that will yield polymer MOF freestanding composite films with favorable properties. These membranes will be used in our electrolysis cell to separate lithium from other monovalent ions that may co-intercalate with lithium in the initial lithium capture step. As mentioned earlier, we are expecting near perfect exclusion from the intercalation material of multivalent ions and other contaminants that are present in the brine solution. Next slide, please. Aside from needing further funding support from this program to advance our solution, we're also making progress to further assess and stage the individual components of our technology. We're moving toward characterization that progressively approaches the actual geothermal brine conditions, but we also need to understand how our technology will fit into existing processes at the Salton Sea. To do this, we will need to coordinate with site and/or facility managers to understand the considerations, constraints, and boundary conditions that we would face upon implementation. Furthermore, we would need to better understand the landscape and nature of technology deployment. In other words, would we be providing unit operations to the site, or would the site lease equipment and pay for recovery of lithium from the brine? All of these details would need to be understood to continue to advance our technology. Next slide, please. Our technology fits well into the lithium market and supply chain. Our packed bed intercalation material-based approach to extracting lithium from the native geothermal brine is a highly scalable solution, and the intercalation approach that we are using involves materials that are abundant and inexpensive. As such, we do not anticipate significant supply chain challenges. Our coupled intercalation process with protected downstream separation processes also enables us to use a closed loop approach to recirculate the redox active materials that drive ion intercalation and release from the intercalation material. This approach further allows us to simplify the supply chain demands for our technology. Ultimately, our technology allows us to capture and concentrate lithium before further purifying it to make a lithium hydroxide monohydrate product that can be sold into a market that is already developed. Prices for lithium map onto product purity in this developed market, so Team Teleport is well poised to target the extraction of lithium from geothermal brine using electroactive intercalation particles that will ultimately facilitate selective and efficient recovery of lithium from geothermal brines. Thank you very much for your time today.
Thank you, Jeff, so much. That was a fantastic presentation. So now we'll go ahead and open up to our IAP members for any questions or feedback that they might have. And IAP members, if you want to just go ahead and unmute yourselves, turn on your camera if you feel like it. The floor is yours. While we're waiting, Jeff, I'll go ahead and kick it off with a few questions for you just to better clarify your presentation. So how could you quantify how your technology and solution will ultimately improve the economics or environmental impact of direct lithium extraction?
So I think to do that further, we need to make a few more advances in terms of developing the next steps of some of the designs in our actual unit operations that we're working on. Right now, we're focused quite a bit on understanding how we can control this intercalation material, what the performance space is there in terms of that material. We're also optimizing our downstream processing capabilities. With that additional information from the laboratory, those should give us the inputs to go through and think a little bit more from a design perspective on more of the techno-economic analysis considerations that would be involved. Our feeling in terms of setting this idea up and sort of creating the roadmap for this technology is that by using this intercalation material as the initial capture medium, we mitigate a fair amount of risk in the process, and we think that will translate into financial benefits in terms of the deployment of this technology. The intercalation material is not particularly expensive, and so we feel like that's a positive factor when thinking about passing a very complex and aggressive brine solution through a packed bed material, whether it facilitates clean in place type processes or facilitates actually just the removal and repacking of the bed. The fact that we're not using particularly expensive materials should be a positive factor there. It also should do a very selective separation on the front end of the process and protect some of our more sensitive components on the back end of the process, which both should reduce the scale and the size of those operations on the downstream processing portion of the technology, just due to the fact that we're able to concentrate lithium from the brine into the solid material and then release that into a more concentrated solution. That should pay some benefits in terms of the overall sort of process efficiency. But to put numbers to that, right, we would need a more detailed techno-economic analysis than we have today.
Great, thank you, Jeff. Are there any other questions from our IAP members on the line?
Yes,
Kevin,
so
you're
Go
far
ahead.
away. Yeah, Kevin Brown here. How do you think your intercalation material will cope with silica, which is trying to deposit onto your material?
I think the audio is a little fuzzy, but I think you asked how we think the intercalation material will handle the silica that may deposit into the material. Is that
Yep,
correct?
that's correct. Yeah.
Okay. So we're certainly aware that silica and scaling from silica is a significant concern. We've been working and talking a little bit with our IAP member about some strategies and from the pre-treatment side of things. Thinking about what the coagulant type processes might look like, or trying to drive that precipitation up front. We're optimistic that we can mitigate those concerns on the front end. Again, at the end of the day, certainly not an outcome we would want to have. But if we did get scale formation in the bed, this would potentially be a circumstance where the bed could be replaced if for some reason the pre-treatment part of the process were to be compromised. But that's still a portion of this that we're working on. We understand this is probably a concern that most are facing as well.
Yep, sure.
Jeff, do you have any temperature constraints with the technology?
Right at the moment, we don't anticipate temperature constraints in terms of our intercalation material. In terms of our downstream and electrolysis and membrane-based processes, we're evaluating those materials at the temperatures that are relevant for the brine situation. So far, we're not seeing issues with thermal stability with the materials that we're working with. So we're optimistic at this point that we'll be able to go to the higher temperatures that are necessary to use the streams as they are and not have to do additional cooling or thermal management.
Thank you.
All right, thank you, everyone. Unfortunately, we'll have to move on to the next one so we can stay on schedule. Thank you, Jeff, so much, and the rest of Team Teleport for your presentation.
Thank you.
All right, so up next, we have Team Goldilocks from the University of Wyoming.
Thank you, Alex. I'm Katie Leoki from University of Wyoming. I'm an associate professor in the Department of Chemical Engineering. So today, you will hear from each of my team member. We have Anastasia and Charles Nye. So Anastasia is a PhD student in my group. Charles is a research scientist at the School of Energy Resources Center for Economic Geology Research. And also Dr. Christel Koloff, who is our associate director for Center for Business and Economic Analysis. So we named our team Goldilocks because we want to use surface engineering and optimal ligand for lithium and other critical mineral recovery from geothermal brine. Next slide, please. So the process we designed is based on best practice out there. Basically, after all we need to do with the existing geothermal plant is retooling. So you just have a T the steam thermal energy will be sent away through the steam to the geothermal plant. We'll take the waste brine and directly to recover lithium and other critical minerals such as barium and strontium. And also the clean water from the cooling tower together with the clean water after we treat our permeate will be rejected back to the reservoir to maintain reservoir health. And then the rest will be concentrated lithium stream, and we'll use the next slide to discuss that. Next slide, please. So the geothermal brine comes into the first module, which it will be a commercial membrane module. to get rid of all the divalent ions, calcium, magnesium, all those interfering ions, we call it. So from this process, we'll end up with a lithium concentrated stream and some of the leftover calcium, magnesium, sodium, potassium ions. And we'll treat the surface by grafting the best ligands out there, commercially available ligands, so we're not making any new molecules. Use the process design, so combinational process design for different conditions to graft those ligands. So that's why we go through different ligands to see which one give us the best flux, because we are making an absorption membrane process instead of using absorbents. So you want to use those ligands on the surface of the membrane to maintain your high flux while capture your lithium and other critical minerals. And then the rest of the water will be rejected into the reservoir. And if there is a need for domestic reuse, we can also do that. So what our goal is to create a process that's zero waste, energy efficient, and cost effective and easy to scale. So we're just using commercially available compounds to do process optimization and testing to make this easy to scale. And during phase 2, we did just that. And Anastasia will share with you our technology development in just a minute. So we tested our lithium recovery capability while maintaining the high flux of the membrane modules. And then briefly, after my team members share with you what they have done, I will wrap it up to share with you my vision for phase 3. Next slide, please. And Charles.
Okay. So as Katie has pointed out, this is a membrane that we're actively making and working to optimize. And so to do that, we had to have a brine for testing that represented the bulk chemistry of the Salton Sea geothermal wells. We included lithium because it's our target. We included sodium because it's the main source of salinity. And we included magnesium because it's been reported to cause problems for other people's processes. We want to give ourselves a challenge. And we also matched the pH in the wells, again, for the sake of challenge and for authenticity. So it was a simple brine, but it matched the real world pretty well. Hand it over to you, Anastasia.
Thank you, Charles. So the first challenge that we faced in designing these surface engineered membranes was to obtain a uniform ligand coverage. Within our first few iterations of our design of experiment, you can see we went from a very uneven coverage on the left to a much more even coverage on the right. Next slide, please. The second challenge that we faced was obtaining ligand adhesion and stability. As you can see on the left, through qualitative visual inspection, we were able to see that we were losing ligand off of our membrane during our testing, based off of the lighter color of the membrane after testing compared to before testing. If you look at the figure on the right, you can see through our iterations of our design of experiment parameters, we were able to obtain a much more stable ligand coverage before and after testing. Next, please. Next and next. So these three show the second method that we used for qualitative color analysis on the stability of our membrane. On the left, showing the permeate after 20 milliliters of water had permeated through our membrane, showing that we're losing some sort of ligand from our membrane. Again, through that process of design of experiment, we were able to obtain a much clearer permeate. Next, please. So the pure water permeance of our commercial neat membrane is referred to as PM0 on the left bar graph, the far left column. And our goal with our surface engineering was not to reduce this flux significantly. We were able to do that after several iterations and keep a relatively high flux that was less than 2% less than our neat membrane. We were also able to obtain a high lithium absorption, up to close to 0.1 grams per meter squared per minute. And now I'll go ahead and hand it off to Christelle for our technoeconomic analysis.
Next slide, please. So the current geothermal operations in the Salton Sea allow for the possibility of retooling existing plants, which would lead to the rapid production of over 130,000 tons of lithium each year, valued at about 1.9 billion. The production process that Katie presented to you today would make a great complement to currently operating plants in that it is easy to deploy quickly, it is scalable, and in a best case scenario would only require a few months of construction and retooling in order for production to start. For our economic preliminary modeling, we're looking at a 50 megawatt geothermal plant that processes over 6,000 gallons of brine per minute, which we think coupled with our production process has the potential of producing 20,000 metric tons of lithium carbonate each year. Next slide. So here on this slide, you'll see costs from other projects that we thought were the most relevant when it comes to benchmarking our production process. The information in the first three columns are from a recent NREL report examining the cost of lithium extraction. In the last column, you'll find our cost estimate from our production process. The takeaway here is that we expect to be able to deliver lithium at a production cost comparable to other projects at around 4,000 per ton. But as you know, this is an ongoing process, so our plan is not just to match, but to improve on the production costs reported by others. In addition, we expect that our production process would require significantly less capital expenditures than other processes currently in development. Now I'll turn it back to our PI, Katie, to wrap up the presentation.
Thank you, team. So using this slide, I will share with you what do we want to do next phase. So on the very left is just lab scale, pallet scale testing, which cross flow. We can do this in my lab right now. And as we move forward, we'll do two things. One is to transfer this surface engineering technology to recover other critical minerals, like I mentioned before. And then in the middle is a commercially available manifold and module setup. That's my goal in the second half of the next 12 months if we get funded to basically test this working with an industry partner. Last is I want to give a shout out to our industry advisor, Mike Sullivan's plant. Actually, previous slide. That's the plant they already deployed in Netherlands. So you missed that. Oh, here, thank you. So Geo40 already has this plant deployed in New Zealand. And also use this opportunity, I want to just highlight the following. We have already accomplished a high recovery rate. So as Anastasia showed you, we can recover 0.1 gram per meter square per minute. Just, you know, after you do the time multiply, and this is just one pass also into the membrane module. So we can recover 110 grams per day per meter squared. And you can do your math if we do more modules in series. Again, this is a low cost process, only use off-the-shelf modules with easy to scale modification. And our target is to have a zero waste so that the geothermal plant folks don't have to request any additional permit by having this process. Next slide, please.
Team Goldilocks, I hate to cut you off, but we're at our 10-minute limit here.
Okay, we're done. So thank you for your attention. Happy to answer questions.
Thank you, Team Goldilocks. So now we can open it up to our IAP members. Maybe I'll go ahead and kick it off again with a question. So can you describe in a little bit more detail the barrier that your lithium extraction process solution addresses as opposed to the current state of art?
Current state of art, best to our knowledge, there's no commercially available such module to recover lithium directly using memory module with this high capacity.
Thank you. And so how does your solution, you walked through the economics, but how does your solution improve or can improve on the environmental impacts of direct lithium extraction?
That's an excellent question, Alex. So right now, if you go back to the slide Christelle used, I think the third last, people use ion exchange or adsorption. So our approach is membrane adsorption, which means we'll use much less footprint. And by definition, by inherent feature of membrane modules, these are very long-lasting, long duration of operation. And also, as a result, all the, in addition to that, all the chemicals we use are environmentally friendly. If there's trace amount of, there's no worry about them causing any harm to the environment. So our design thinking is to make it green and make it zero waste.
Thank you so much. Anybody from the IAP want to jump in with any questions or feedback for the Goldilocks team?
So Derek, with ESM here, so you did mention kind of the brine chemistry profile that you used as a surrogate. Are you looking at maybe doing some additional test work with maybe a little broader spectrum and throwing in maybe some transition metals, some other things in there as part of the test program?
If I may, Katie.
Yep. Go ahead, Charles.
Yep, definitely, Derek. And that's our hope for the next phase, is that we could make this even more authentic, maybe boost the temperature a bit, get some silica in there. As the other people have pointed out, silica is a big challenge. Again, we think we can handle on the front end, but why not simulate a little bit of it slipping through and see if we can handle that? We'd love to boost the challenge on ourselves.
And I guess I asked previously, do you foresee any temperature limitations, or can you operate at elevated?
The commercial modules we selected, they can tolerate high temperature. Well, 120, 160 degrees Celsius. The geothermal come from the flash unit is not a problem. And also, Derek, I just want to make a comment because I know you asked Jeff this question. For silica, as our industry advisor was telling us, you actually can make colloidal silica as another stream of product. So turn lemon into lemonade. Just want to make that comment.
Very good.
Thanks, Derek. We have about a minute left. Any further questions from our IAP members? All right, well, with that, we'll go ahead and thank Team Goldilocks again for presenting today. And we will go ahead and move on to our next team. I'm gonna need help with some of these team names. So from the University of Massachusetts, Dartmouth, we have Lyrics Nano. You have to help me out, team captain. Lyrics. Great, thank you so much.
Different spelling.
That's very creative, thank you. Go ahead.
Thank you, Alex. We are very excited to discuss Lyrics Nano, which is an acronym for lithium recovery using ion exchange and nanofiltration. Next slide, please. We are Team Sengupta, but just for full disclosure, though our last names are same, we are not related. But combined, we have more than 60 years experience in designing and operating such systems, water treatment systems, for example, soup to nuts, from developing material to testing it in bench scale to testing in pilot scale, and then putting them in real scale units in a variety of countries under some very challenging conditions. So we have all the infrastructure, analytical, etc., that is needed for a project like this. And we also have experience with technoeconomic analysis. As you know, in such kinds of systems, typically we say that about 2/3 of the cost is from materials and reagents. So as I will show in subsequent slides, we have a very competitive process because the reagent usage is very minimal. Next slide, please. So the highlights of this process are we have adapted it to the very unique characteristics of the salton-sea brine. So salton-sea, as we know, there is an electricity generation plant there. So it is generating electricity and we use that electricity. And the salton-sea brine, of course, has very high chemical potential. So we use that osmotic pressure as our draw solution for the forward osmosis part. And the only chemicals that we are using are hydrochloric acid and sodium hydroxide, both of which we generate at site using electricity and electrolysis of the brine. And finally, we have talked about the thermal energy of the brine. We are harnessing the thermal energy to enhance our process efficiency, especially in the regeneration of the ion exchanger systems. Next slide, please. So as you know, this is taken from open literature, salton-sea brine. You see it has lithium, about 200 milligrams per liter, but 50,000 plus sodium and very high calcium and very high potassium. And so we have mimicked a solution, not with all of these constituents, but with the majority of the major constituents. And I'll now walk you through our process. Next slide, please, which is an animation slide. So Lindsay, when I say go ahead, please do so. So we bring this salton-sea brine, as we just heard in the previous talk, and we first pass it through a nanofilter. And the main job of the nanofilter is to reject divalent cations. So this reject then goes back into the well, and we get a stream which is monovalent cation rich. Of course, it has lithium, but much higher sodium and potassium. So this stream we bring in contact with the specialty material, which is very selective for lithium. And this stream is passed through this material and it picks up selectively lithium, but because there is so much competition from sodium potassium, it does pick up some sodium potassium as well. So we regenerate this material with HCl from electrolysis of the brine. Now this HCl, of course, gives us a very low pH solution. And we then take this solution and pass it through an anion exchange membrane where, go ahead, Lindsay, please. This anion exchange membrane, all it does is it picks up the H+. So the pH was very low. Now it is near neutral. And this we then bring back to our selective adsorbent material. And we do this multiple times. Our Goldilocks, on the second presentation, our Goldilocks is about 3 times. So after 3 times of this, we then have a solution which is very rich in lithium. It does have sodium and potassium as well. So this solution we bring in contact with the cation exchanger. And because of certain chemistry and conditions of operation, what happens is that lithium elutes out of this exchanger through what is known as chromatographic elution. And it comes out at a concentration much higher than the concentration you're feeding in, and it comes in alone. So this stream we capture, we pass it through an anion exchanger, which exchanges the chloride and sulfate and all the other anions with hydroxide. So we get a pure lithium hydroxide, which we further concentrate using a forward osmosis process where, Lindsay, go ahead, please, where we have our draw solution as the salton-sea brine, very high osmotic pressure. So water moves across the membrane and go ahead, Lindsay.
Next slide. Are you ready to move on to the next slide? Did we lose our team lyrics? Lindsay, we might have lost our team there. Is there anybody else from the team lyrics that could fill in?
Yeah,
jump?
please go
Thank
ahead,
you.
And then, so this is the summary, which is self-explanatory, that this is the feed, which is solvency brine. We get pure and concentrated lithium hydroxide. This is the product. And most of the chemicals which are being used, they are coming from solvency brine. They are primarily hydrochloric acid and sodium hydroxide. They are coming through electrolysis of the solvency brine, with the electricity there. And the lithium pre-reject, which is left after the treatment, it is being re-injected, So it is environmentally, at least, looking very benign, because we are taking advantage of sodium chloride being electrolyzed, producing sodium hydroxide and hydrochloric acid, and getting lithium hydroxide as opposed to lithium carbonate. So this is the overall kind of panoramic view of the whole plant, snapshot. That's basically it, Shikalani is probably back, so please go ahead.
Yes, sir.
I believe this is the last one.
I'm sorry.
Okay.
Just to highlight what Professor Sengupta was saying, that we are recovering more than 90% of the lithium in the brine at greater than 99% purity, the goals. And because the only chemicals that we are using, hydrochloric acid and sodium hydroxide, are generated at site through electrolysis, we believe we have a very competitive product. And we want to have minimum water usage. We just heard Sue at the beginning that the water usage and carbon dioxide footprints are major criteria. So we do very well in both these criteria. So next slide, please, Lindsay. I will skip this. Next slide, please. I'm sorry, we are running out of time. So the value proposition, as we just heard, we are utilizing the thermal energy of the brine. We are utilizing the osmotic pressure of the brine. And we are utilizing the electricity generated at the solvency site for the only two chemicals that we need. Next slide, please. And we are, as we just heard, we are directly generating lithium hydroxide without intermediate LCD, lithium carbonate. So we have synthesized this adsorbent, which is the lithium manganese oxide, and we know now the values of X, Y, and Z, which are the best for this system. We have developed a kinetic model for the ion exchanger regeneration at elevated temperature. And we would need the real solvency. We have mimicked that solvency solution, but we need the real water, which we know as part of phase 3, we will get something that very closely resembles it. We do need pilot scale facilities to get the design parameters and benchmark our technology against other companies. Thank you.
Thank you, Team Lyrics. Okay, now for some questions and feedback from our IAP members.
Kevin Brown here. Have you estimated the amount of electricity you'll need?
The amount of electricity we need kilowatt hour per meter cube of water treated is very competitive. I cannot give you a value, but because this is a very high concentration sodium, very high sodium chloride concentration brine, our electrolysis efficiency is very high.
Right, okay. Thank you.
It's Mike O'Sullivan here. Your water usage is, have you got any ideas of how you can reduce that? This is pretty
The
high.
usage of hydrochloric acid and sodium hydroxide?
No, the usage of water. You said 20 gallons of water per 100 gallons of brine.
Yes, yes. So the water, fresh water usage is for these regenerant solutions, the hydrochloric acid solution that we are. So again, it is a function of the concentration and the amount. So as of now, I think we are very comfortable with 20, but that's always the challenge, to keep reducing it without compromising on process efficiency.
Thank you.
Thank you.
I'll jump in here with the question. How is your solution addressing environmental impacts of direct lithium extraction?
So Alex, as we just heard at the beginning from Sue, we want to have minimal water use, which we talked about. There is no carbon footprint of this because, again, the electricity that we are using is from the geothermal brine, renewable electricity. And we do not bring in any chemicals. We do not have pretty much any waste product. So it's kind of a zero waste system, except for after many, many cycles, this ion exchanger may have to be disposed of. The material, the lithium manganese oxide material may have to be disposed of, but that is after many, many cycles. So we believe its environmental footprint, its environmental considerations are very favorable.
Thank you.
Thank you, Alex.
Any other questions from our IAP members? Another question for me is, how did you work with your IAP member to advance your design?
Gave us a very good idea of what are the challenges, especially something that we've talked about in the earlier presentation, the silica challenge, how we can, what kind of a pre-treatment may be needed if the nanofilter doesn't work. So that we got.
I think we lost Team Lyrics again. Do you want to fill in there?
Yeah, we had only one meeting, you know. The other thing was that the cost of the chemicals, you know, that always determines the economics of the process. So that's when we talked about or came to finalize that we'll be using sodium hydroxide, hydrochloric acid being produced from the this feed saline water. So there, you know, he was pretty agreeable, and that was a plus. Regeneration efficiency, we discussed about that, and similar kinds of things, you know, like some kind of ideas or some kind of clickers, you know, which kind of helped us to refine things.
Great. All right. Well, thank you so much, Team Lyrics, and all of our teams that have gone so far. I think, Lindsay, we due for a break here? Fantastic. All right. So, Lindsay, can you go to the next slide so we can see who's up next? That way that team can get prepared. All right. Oregon State University, you're up next. So, as Lindsay said, we'll do a 15-minute break back at 4:10. What time is it now? 4:10 Eastern. So you can go ahead and leave your keep logged in, but please mute yourselves. And we'll see you back here in a few minutes. Thank you. All right. Lindsay, are we ready to get started again? Oregon State University, are you on the line?
Yes.
Great. Can you help me with your team name so I?
Yes, Espica.
Okay. Didn't sound right coming from you. So, well, thank you. All right. If everybody's back online, we'll go ahead and jump in whenever you're ready.
Good afternoon, ladies and gentlemen. Thank you very much to you all and to Geothermal Technologies Office for this opportunity. My name is Baman Abbasi, and I lead Espica, which is a spinoff from Oregon State University. We are a lab based in Bend, Oregon, and we specialize in brine treatment and low-grade energy recovery and production of high-grade mechanical work from it. Our project is titled Production of Lithium Carbonate and Hydroxide using geothermal brines. And this draws on our team's expertise in 4 areas. 1, using low-grade thermal energy to produce high-grade mechanical work, our existing IP and then technologies on solar-driven treatment of brines, high salinity, 10 to 30% salinity brines with zero fouling and little liquid discharge or no liquid discharge. Our partners at the University of Nevada specialize in sustainable mining, and our advisor at USGS in geothermal lithium. Next slide, please. You all know the scope of the problem. We have a table here to show some of the main geothermal and continental brines in the US. A lot of potassium salts, sodium salts, very low concentration of lithium salts. So where we come in is on the very upstream in order to get this low concentration lithium and increase that brine, that concentration of lithium in the brine to 5,000 to 7,000 or more if needed, ppm, in order to extract lithium carbonate and hydroxide. Currently, one of the most important ways or most common ways that they do it, primarily in South America, is using solar evaporation ponds, which take a very long time. So they cannot really respond to market fluctuation, market needs in real time. They take a lot of real estate. They deplete some water resources because they just let them all evaporate. They cause aquifer compaction and all the rest. And it is in part because of this that about 99% of our domestic lithium consumption is important. Next slide, please. So our proposed technology draws on the expertise that I told you earlier to use low-grade heat, which is abundant in those settings in terms of low concentration solar, or this is Geothermal Technologies Office, geothermal energy, to use heat in the range of about 200 degrees Celsius to pressurize the brine and use a 2-stage treatment. 1, if appropriate, use a reverse osmosis if it proves to be efficient enough. And then we will pass that through our proprietary and patented desalination technology that uses atomization and humidification to produce clean water and zero liquid discharge. So basically just solid salts. Under this project, we will extract some solid salts, but we will evaporate the brine efficiently such that the concentration of lithium reaches about 7,000 ppm. And on the downstream, we will treat that brine to extract lithium carbonate and hydroxide. What progress we have made so far? Our thermal compressor has been fully demonstrated. We are improving its efficiency, improving its pressure, and it's a dual loop fluid, how it exactly operates under these conditions, but it's done. Our anti-clogging atomizer, which is really important for efficient atomization, has been proven that it can atomize 20 or more % salty water with just about no fouling over 14 plus hours full working cycle. We have demonstrated our cyclonic separator with no fouling, extracting solid salts from the brine. And for the next phase, phase 3, based on our IAP recommendation, we will really look at whether or not there is an RO system that is suitable for this, or even if we need it. We included it only for efficiency purposes, but we will investigate if it's appropriate or not. And if it's needed, we may or may not keep it. We will tune up our thermal pump. We will tune up our control system to make sure that we evaporate just enough water to concentrate the lithium. And lastly, we will focus on efficient extraction of lithium carbonate with the purities that are needed. Next slide, please. So what do we contribute? We are at the very first step of the supply chain. Our competitors are solar ponds. You all know about that. Passive solar, minimal maintenance. There are some good things, but the long time and all the things I said are the downsides. There are ion exchange as well as electrodialysis. I'm going to skip through that because you know that well, but what I want to emphasize is what we contribute is just about no electricity. It is entirely thermally driven. It is modular, it is portable, it is scalable. And we do not need a lot of existing energy infrastructure. If there's existing geothermal, great. If not, we can use very inexpensive solar collectors just to concentrate solar energy a little bit. If you have other industry around that produces heat at about 200 C, which is very, very common, it's commonly treated as waste heat, we can utilize that. So that's the value that we contribute. You don't need to build anything for this process to operate. Next slide, please. This is a schematic of our system. I said modular. You see two modules here in a container. So what we envision for this is a traditional 40-foot container or 53-foot container which has multiple modules in it. Each module has the thermal pump, which is shown as the bronze component, which is done, potentially the RO unit if we need it, and the desalination unit, which is the more complicated looking one at the middle, which is also fully demonstrated. What we put into the system in our treatment container is the brine feed and heat. What we get out of it is the brine with high concentration of lithium. We get some solid salts and we get clean water. And what we can do with that clean water is either utilize it locally when needed or put it back in the aquifers to prevent compaction and pH adjustment and all the damage that just extracting will do to the formation, which is part of the reason that we cannot really permit these so easily in the US. Next slide, please. So our team, myself, Baman Abbasi, Dr. Durga Prasad Ghosh, who is also on the call at ESPCON, Oregon State University, University of Nevada for Sustainable Mining, USGS and Nevada, Dr. Lisa Stillings, who specializes in geothermal and continental brines, Dr. Howard Brands, who is advising us on commercialization and technology assessment. And we have communicated with multiple companies, commercial entities in the field. We have some letters of support, and we are actively working toward our design and securing the required funding to address our technical risks and challenges. Thank you very much.
Thank you, team. All right, we'll open it up to IAP members.
So Derek with ESM here. So I'm going to flip my temperature question. On the process schematic in that container, you noted you're going to have a heat input. So, you know, the salt and sea geothermal brines are typically over 100 degrees C already. What's the preferred temperature range if it's higher than that?
If it's a little higher, well, we can heat it up a little bit, because if it's already 100 degrees Celsius, we might honestly not need a lot of added heat. What we do is we use an air blast atomizer, and that's how we humidify this. Right now, we're doing this not for geothermal brines, for highly concentrated seawater, and we're doing it at about 80 degrees Celsius. And that's just enough to humidify it, because we don't boil anything, it's just humidification. So already at that temperature, given that we add a lot of air to it, so the temperature will drop a little bit because of the wet bulb temperature. We just make sure that it reaches its humidification point, and we will adjust our heat temperature accordingly.
And just for clarification, that's after the power plant. So not
That is correct. That is correct.
Yeah. Okay. Thank you.
Thank you for the question.
The floor is still open for our IAP members, but I'll jump in with the question. For phase 3, can you describe to us how you would plan on testing your technology?
That is correct. So we have made some contacts. Number one is we have a letter of support, and they have operating plans in Bolivia and elsewhere. They've promised as much brine as we could use. So our brine supply, we considered it settled. Here at OSU, we have a campus that can handle these containers. Just during the spring break last week, I was there talking to them to make sure that we have the space and all the infrastructure to run the container. In addition to that, Beggendorf, which I'm sure you know about, down in New Mexico, we have contacted them. They have given us a quote as well as the facilities that we could possibly use. Even though they specialize in brackish oil and gas water, we can do some solar or geothermal studies over there because they have all the disposal means and methods. Here, our lab, we will do a lab scale module demo. But for real size phase 3 demo, we will either do it at Beggendorf or at OSU's Hatfield campus, which is on the coast and really can handle these large scale demonstrations. Does that answer your question?
Yes, thank you. Sorry, apologize. Yes, absolutely. Thank you.
Thank you.
Another question I'll throw out to you is, how does your design improve upon the economics of the current state?
So yes, that is a little difficult because we can look at the spot price or the contact price of lithium. So the contact price that we were given through our contacts is a range of 5,000 per metric ton. Our best estimate is that we can beat that by about 30%. But if we look at the spot price, it was about, I want to say 15,000 per metric ton. So vastly less than that. What I would say is I'm not really harping on our economics, except to say that we will come out below whatever the current market price is by a good percentage, 30% or thereabouts. What we really contribute is we can do it really quickly, modular, scalable, portable, so we can respond to market fluctuation and needs whenever needed. And we save a lot of environmental impact and damage, so we can actually permit these things and get them running insolvency and elsewhere in the US without environmental damage. That's really where we contribute value.
Thank you. And with that, if there's no other questions from IAP, I can pause, but please jump in if you have other questions or feedback. So you're saying for phase 3 that you can be flexible and test your design, whether it's in oil and gas setting or in geothermal insolvency. Those environments are two very separate systems. So how do you account for temperature specifically with your design?
So we need to specifically design for the temperature, but it is honestly such a low temperature that you can, if it's a low hot, we can dissipate a little bit of the heat, or if it comes a low low, we can augment the heat. When we talk about 200 C, it's such a low temperature that handling that, we have not considered it as a big challenge, but based on your feedback, we will focus more on it to make sure that we will get the temperature right. But if it was 600 degrees Celsius or thereabouts, then we would really have a problem. But I don't see how at such low temperatures it would be a big issue. But we will focus on that for sure.
Thank you.
Thank you. Thank you.
All right, we're just about out of time. Any other questions from our IAP members? All right, well, thank you so much. Next up, we have MIT with Team Nanoporous Graphene Membrane. You can go ahead and jump in whenever you're ready.
Hi, good afternoon, everyone. Can you hear me?
Yes.
Great, thank you. So it's a pleasure to present on behalf of my team. Next slide, please. So the basic concept that we are developing is nanoporous graphene membranes that can selectively enrich lithium over other ions and do so in an ultra-fast filtration manner. As seen in the schematic here, what we have is an atomically thin material with precisely drilled holes in it that we can tune and thereby control what species pass through it. And so the idea is we can use these to efficiently enrich or concentrate lithium, either reducing the cost and environmental impact of upcoming direct lithium extraction technologies, or eventually replacing them altogether. So in phase 1, so we have experimentally characterized and shown selectivity between lithium and other monovalent ions, so mainly potassium and sodium, which are dominant in the Salton Sea. We have identified certain opportunities for use of membranes to enhance emerging DLE processes. And then we also published a journal article in Advanced Materials that showed how we can tune the pore size distribution in graphene. So basically, we are essentially selectively cutting off the larger pores that enhance selectivity, and then we can obtain ion-ion selectivity as well as desalination by this method. Going on to phase 3, we would like to further develop and characterize the membranes in model solutions as well as Salton Sea samples, and hopefully fabricate modules and also do a preliminary technoeconomic analysis. Next slide, please. So we all know that lithium demand is growing and it's critical for a green future. And the global supply currently is dominated by only a handful of countries, and the production in the US is low. But if you look at the total reserves in the US, it's almost on the order of 11 million tons, and most of these occur in brines. Next slide, please. And recovering lithium from brines is challenging, as this group knows, and that's because of the lower concentrations of lithium and the background of other salts, and also the environmental impact and challenges associated with conventional extraction by evaporation, which uses up land, creates sludge, and it's not so viable in the US. And so we have a need for new technologies that address these challenges. But many of the direct lithium extraction technologies that are under development either require energy consumption or reagents, for example, to regenerate sorbents. Next slide, please. So we are exploring this new material, nanoporous graphene, that provides unique opportunities for advanced separations. And I've just tried to list some of the key advantages here. So because this material is really thin, the effect of that is the very low resistance to flow, and that can enable more compact and more energy efficient systems. The carbon lattice in itself is mechanically strong and has good chemical stability, and that translates to the ability to withstand high pressure. And so one can even envision systems in the future that would concentrate saturated brines. The high chemical resistance translates to being able to operate with a wide variety of process streams and better fouling control and longer membrane life, which are some of the challenges in geothermal brine lithium extraction for membrane-based applications. The pores in the carbon lattice are amenable to rational design. And so we have developed some ways to create pores and tune the pores, and we can basically tune selectivity by this way. And because the separations are based on transport, there is no need for reagents or solvents, and that translates to lower environmental impact. And finally, graphene itself and the membrane processes are scalable, so we can do roll-to-roll synthesis of graphene, which has already been shown by several groups. And so that lends itself to scalable manufacture, and that has potential for offering precision at a reasonable cost. Next slide, please. So what's the opportunity? So one is basically to reduce cost and improve the quality of product, and also mitigate the environmental footprint of emerging direct lithium extraction technologies. So this is one example where I've shown three stages in which where these membranes could be used. So one is before lithium extraction, it might be possible to actually concentrate lithium over sodium and potassium and other ions that compete with ion exchange or sorbents, and thereby reducing the amount of sorbent and the associated reagents and the costs for the lithium extraction step. The other possibility is after elution, when lithium has to be concentrated, reverse osmosis is already a step in this particular flow, but basically we could use these membranes to push up the concentration and reduce the energy consumption for evaporation. And finally, at the last stage where lithium is purified, these membranes could further reduce other impurities and enrich the quality of the lithium product. Next slide, please. And eventually, I've titled this a moonshot. It may be possible to just directly do a two-stage lithium extraction. And on the left, we have basically a list of the ions commonly found in the Salton Sea brine. And you can see that there is a range of hydrated ion sizes, as well as the major ions that compete with lithium. In this case are calcium, sodium, and potassium. And so one can imagine two process stages, either including membrane cascades, such as the one shown at the bottom, or with further development of the membranes. If we get high enough selectivity, maybe we don't need big cascades. That could then enrich lithium and directly produce a concentrated stream of lithium by separating out other ions with relatively low consumption of reagents. Next slide, please. So this is just a very broad level comparison. So if we look at solar evaporation, the main drawbacks are the high land use and low throughput. With adsorption-based technologies, those work very well, but there is a chemical use for regeneration of the adsorbents. And similarly, electrochemical separations, you can have higher energy consumption. And so membrane-based technologies are attractive, and in particular, nanoporous graphene has the potential of being both chemically robust as well as tunable selectivity and high permeance, so it easily allows transport. Next slide, please. So we have been working on this technology for a decade or so, starting from scratch. And here, basically, we have just listed some of the key advances, including being able to create sub-nanometer pores very accurately, designing membranes that are defect tolerant, and being able to tune the leakage pathway so that we can get functional membranes even when we have an atomically thin layer. And recently, we have shown desalination ability to have selective transport at the sub-nanometer scale, both in liquid and gas phases, as well as monovalent ion selectivity, as well as stable operation at 100 degrees, which is published. And we have ongoing experiments with some other separations at about 200 degrees Celsius. And we also have a broad IP portfolio. So the picture shows the graphene membrane, and on the right, top right, this is an experiment where we basically cut off the tail of the pore size distribution, and we can see the rejection of sodium chloride changing as we tune the pores. And we can also see selectivity between sodium chloride and magnesium sulfate in this case. On the bottom left, we can see lithium versus potassium, rubidium, cesium. We can see selective transport. And on the bottom right, we are able to basically have liquid transport that's very selective at the sub-nanometer scale, where we can separate out branch from linear molecules. Next slide, please. So in terms of outlook, on the right, we have the desalination capacity, and we can see that the reverse osmosis membrane-based capacity has gone up while the others have saturated. And so advances in membrane technology have led to replacement of thermal-based methods with membrane-based methods. And so if we are able to make similar advances in membranes for these applications, then it is possible that we can design new kinds of processes that may be able to replace some or many or most of the unit operations in direct lithium extraction. And just as a cost comparison, so seawater desalination is about $0.5 per meter cube, and if we have lithium at about 200 ppm, that translates to about $2,500 per ton of lithium. And
I hate to interrupt, but we're a little bit over time. Do you want to do a quick wrap up?
This is the last
and then
slide.
We'll open it up for questions. Okay.
Yeah. So I'd like to acknowledge my team, also our IAP advisor, Derek, and I'll conclude here. So thank you for your attention.
Thank you so much. All right, we'll open it up to our IAP members for some questions and feedback.
What's the highest temperature that you could go to with your graphene?
So it depends on the kind of solution. So if we have oxidizing, like oxygen present, we can go roughly around, at least we have done experiments about 200. And when we expose it to oxygen at high temperature, we start, or at least based on literature, around 400 degrees Celsius, we should start to see issues. So in the 200s, there is no issues.
Oh, excellent. Thank you.
And so Derek, here, you mentioned that the graphene has the ability to operate at higher pressures. What do you think are the sort of the operating limits there?
So for graphene itself, the limits are pretty high. I think that it would be limited by the support on which it is placed, as well as the high pressure infrastructure that goes around it. There were simulations by one of my colleagues here at MIT, Jeff Grossman, and then we did follow-on experiments where we measured the ability of graphene to withstand a pressure difference. And what we saw is that if you have the right support design, so let's say a few nanometer or 10 nanometer, 20 nanometer scale pores in the support, then potentially you could go several hundred bars, maybe more. Yep. So the graphene itself is not the limiting factor in going to high pressure.
Mm.
Will the graphene foul with silica?
I think any membrane fouls. So I think we should expect some degree of fouling, but also the ability to, the chemical stability opens up the possibility of cleaning it very effectively. And of course, I think we would need to do experiments with the actual brine samples to be able to see the extent of it and whether we need, to what extent we need clarification and pretreatment. So we don't know that at this point.
All right, we're almost to time. Are there any final questions for Team Nanoporous Graphene? All right.
Thank you.
Thank you so much. Just quickly before we get started, I want to just make note that in the chat box, several of the team members have been sending questions for other team members. So be sure to check out the chat box. Somebody might have some information or a question for you. So, all right, next up, we have Miami Solution from the University of Miami. Whenever you're ready.
Yes, I'm ready. So actually, our team is specialized in electrochemical processing and electrochemical power sources like fuel cell, batteries, and supercapacitors, the hydrogen production, and so on. Okay, next slide, please. So we want to call this technology as innovative, efficient, and cost-effective electrochemical extraction of lithium from brines. And this technology actually includes three new concepts. First, high capture rate and low pressure drop flows through electrochemical reactor. Second, novel method for fabricate and uniform ultrastate electrode. The third, and the unique alternating use of lithium selective and rejective process. This technology promises high production rate, high efficiency, and low cost extraction of lithium from brines. We did something in the phase one. We actually have designed the bench scale flow through reactors and fabricate high quality thick electrode, conducted single cell test for selectivity and rejectivity electrode materials evaluation, and evaluate the corrosion resistance for the current collectors. And finally, we established the formulated method for cost estimation. In phase three, upon demonstrating feasibility and optimizing the technology and the cost evaluation in phase two, we're going to scale up right away the reactors to build a system with a production rate of 22 kilograms per day and test it with pretreated brines. And then we're going to manufacture a movable skid of 10 reactors and test them with real pretreated brines. And then finally, we're going to assemble a skid of 72 reactors with production rate of 1.5 tons per day and conduct pilot scale on-site testing. And we have industrial partners, potential industrial partners. Actually, we are happy in providing brines, technical support, and manufacturing assistance. Next slide, please. Next slide. Okay, thank you. Here, go back. Sorry, go back. In the phase two, we're going to demonstrate the feasibility, and we are going to design, fabricate, optimize the electrode reactors and the system, evaluate the sensitivity, selectivity, sorry, production rate, efficiency, power, and water consumption, and durability cost as a function of property of the brines and operational parameters. Also, we're going to design a pilot scale system and project the cost for industrial production. And the merit of the technology is as following. First, voltage and potential control will end up with very high, I think as high as the kinetic, reaction kinetic, and highest selectivity. Second, the design of the electrochemical reactor adopt a low pressure drop and a high capture rate configuration. And the third, actually we can fabricate a thick electrode that will reduce the assembly number of assembly and then reduce the cost. Fourth, the alternating use of lithium selective and rejective reactors increase the efficiency and reduce the number of processing cycles and the cost. And we project the production cost right now is less than $1 per kilogram for lithium carbonate equivalent. And we think this is much lower than those of existing technology. Next slide, please. Next slide. Okay, this is our design. On the right is our design using the Teflon. We can actually reinforce with metal. So this is suitable for high temperature operation. And on the left is the schematic, and we can bring the brine inside of the reactor, and the brine flow will be separated in the different cells, which is in this stack, like a battery stack. And then the flow actually goes through lithium selective and count the electrodes. And in this case, the reaction design offer high capture efficiency, low pressure drop, and low void volume. And in this case, we can have high recovery efficiency and low consumption of power and fresh water. Next, please. So alternative operation for lithium selective and rejective, I think is the new idea. And as you can see from the right side, this is the state-of-art technology. And however, if they only use lithium selective reactors, in this case, they need at least 5 cycles to reach 95% purity. But in our case, we can first use lithium selective to reach lithium ion and the other ion ratio 1.0, about 1.0. In this case, in the second cycle, we're going to use rejective purification step. And in this case, other ions will be absorbed. In this case, we just let the lithium go through and collect it. In this case, we can easily get 95% purity. Next slide, please. So the thickness of the electrode is also very important, because if we can increase the thickness of the electrode, you can actually reduce the cost, reduce the 75% of cost for materials and maintenance. However, making a thicker electrode is not easy, because you can see that in the battery industry is very difficult. And the highest thickness is about 200 micron, free of cracking and low resistance. So we developed a new technology that allows us to fabricate crack-free and low resistant electrode with 900 to 2000 microns. Next slide, please. Next slide. Okay, this is our design, detailed design. Next slide, please. Next slide. This is the system design, and this we have. This is selective reactor. This is rejective reactor. So computerized system will control this critical parameters, so we can have very tight control of the process. Next slide, please. So this is the thick electrode we fabricated. This is single cell testing equipment setup. Next slide, please. So we use electrochemical impedance spectroscopy to measure the resistance, and you see the resistance is very low. And in the left side, we use a cyclical voltammetry to test the relative selectivity. And we can actually play with the cell voltage to figure out the highest relative selectivity. So for example, the selectivity to lithium is 160-fold greater than that to sodium. And that is very good. Next slide, please. So we use push and blow as a rejective electrode, and we can find out the selectivity of PB to sodium is 10-fold greater than that to lithium, which is very good too. Next, please. So this is our project cycles. Using the new technology, we just need 2 cycles. Using the old technology, we need 4 or 5 cycles. Next slide, please. So we also test the corrosion resistance, and we found that for titanium is very good. The general corrosion rate is less than 1.5 micron per year, which is definitely acceptable for this task. Next slide, please.
As Dr. Zhou pointed out, we also performed a techno-economic analysis to estimate the final lithium carbonate and final lithium hydroxide cost. To this end, we considered 2 production scenarios, having production rates of 1 and 100 kilotons per year. In the analysis, we included the electricity, pumping, consumables, and equipment costs, while well expenses such as pumping and drilling are not considered. Next slide, please. Our financial analysis showed that for the production rate of 1 kiloton per year, the final lithium hydroxide cost could be about $1 per kilogram, whereas for the production rate of 100 kilotons per year, this could be reduced up to around $0.7 per kilogram. Next slide, please. In fact, these lithium carbonate costs are up to 87% lower compared to the conventional solar evaporation process. And this process also provides a cost advantage over the current state-of-the-art methods, including Energy X, membrane separation, and Lilacs ion exchange technologies. In addition to the cost advantage, the process could shorten the processing time from 18 months to below 2 hours and increase the recovery rate from 30% to 95%. And with this, we would like to thank you for your attention and like to have your questions.
Thank you very much. All right, we'll open up the floor to our IAP members.
Yep. So Derek here, I guess as you're looking here at the economic calculation, trying to get to the dollar per kilogram, what's the biggest driver here? Is that efficiency, power, less power consumption? Is it higher recovery? What do you think is the bigger contributor to that economic benefit?
Yeah, thank you, Derek. Our biggest contribution for the cost is our consumables, such as electrode materials for the reactors. Our own technology, actually, since we are experts in the supercapacitor electrodes and supercapacitor technologies, our electrodes much more durable compared to the conventional battery electrodes. So we could save some consumable costs from there. But in our cost calculation at the moment, is the main cost contributor is consumables.
Can I say something? So electrochemical process, this process is very fast. So in this case, all the time sensitive cost can be reduced and minimized.
So the floor is still open for our IAP members, but I can go ahead and jump in with a question. Question is how does your solution improve on any environmental impacts from the current direct lithium extraction technologies?
I think our technology actually, I just realized we don't need the pumping, so we can save the pumping power. And the temperature, we like high temperature to increase the kinetic. So in this case, we can reduce the signature, carbon oxide dioxide signature. And you have a Mert and Hongtan, do you have any comments?
Yeah, let me add, maybe I can add. Actually, if you look at the process, we have a two-step type process. The first step is lithium extraction process. After that process, most of the fluid, almost all of the fluid, except the lithium enriched in the catalyst, in the electrode, are rejected back to the well. There's nothing to the environment. So, and then we only process those extracted places. Since it's the flow through, we can extract almost all the lithium ions from the first process. And the second process is taking, out. So that's, I guess, maybe Shaya maybe can elaborate on that. Right?
Yeah, I have another point is that the use of Prussian blue is really very advantage in reduce the power use. Because as you can see previously in my slide, so for the selective reactor, we need 0.6 volt. But for the rejective reactor, we only use 0.13 volt to get the highest selectivity. in this way, we can significantly reduce the power usage. I think that will reduce the signature.
Yeah, I can also add a few points to Dr. Joe. As Dr. Joe mentioned in the process, our process is actually thermodynamically feasible, meaning during the adsorption of lithium, we don't really need any energy input. We only use the energy in the desorption of the lithium. So that means we need to apply minimum energy for the total process. And secondly, as far as the environmental elevation of the environmental problems, the other state-of-the-art technologies also employ acids. So in this process, we eliminate the use of acid process, and this, for instance, Lilac has such sort of process. Thank you.
Thank you so much, Miami Solutions. All right, we'll go ahead and move on to our next team. Up next, we have the Bruce Parkinson's team from the University of Wyoming. And whenever you're ready to go ahead and get started.
Yeah, go ahead. First slide, please. All right, so we're a team from the University of Wyoming, John Hoberg and Jonathan Brandt and myself. Next slide, please. Here's a picture of us in the John Brandt lab, who has a very highly outfitted laboratory for both membrane characterization and scale up. And on the right is John Hoberg, a synthetic organic chemist, and you'll see how there's a feedback between him and making the membrane materials, and Jonathan Brandt as membrane engineer and scaling up. Myself, I'm an electrochemist by training and do a lot of material science. So we think we have an ideal team of senior investigators to approach this problem. Next slide, please. So our approach focuses on preparing novel two-dimensional, what are called covalent organic framework materials that are very highly ordered and very robust. And we can chemically modify these materials very precisely and very rationally to change both the pore chemistry and the pore size. And they're also 2D materials, so they are very naturally fabricatable into membranes. And like graphene, they can be very, very strong. And you'll see the structures are very similar, but much more ordered. And so in phase one, we've been continuing to develop new materials and beginning our membrane testing for selectivity between lithium and particularly sodium ions. And by phase two, we will hopefully have zeroed in on the ideal 2D COF material and then start to build small-scale chloralkali electrolysis cells to then be able to scale up for phase three or basically a pilot level demonstration. So the next slide shows a very simplified diagram of the key idea in this particular team. And that is producing the lithium hydroxide in one step. In addition, we're going to be able to produce green hydrogen and either chlorine or oxygen, whichever is more efficacious at the location. Chlorine is an industrial levels material that has value, as well as green hydrogen being, of course, if this is using the geothermal plant's electricity, has a higher value than normal hydrogen. So the whole key here is the fact that we make in this chloralkali electrolysis cell a lithium selective membrane, so that when the electrons are going one way, the only cation that can go the other direction in order for electron neutrality is the lithium ion. And so what we do is we end up with a lithium-rich brine going into one side of the cell and a lithium-depleted brine coming out. In principle, however, we do need to pre-treat this brine to get rid of the silicates and the iron silicates, and perhaps even do a magnesium and calcium carbonate precipitation, although we could still tolerate separating lithium from magnesium and calcium. And how we do that, okay, so you see then there's this water going in, lithium hydroxide coming out, plus green hydrogen, and either chlorine or oxygen in somewhat conventional chloralkali, which is a scaled industrial process. Next slide, please. Next slide shows a space filling model of our 2D COF membrane materials. And this particular one has sulfonated groups in the pores, so it's somewhat like Nafion in terms of being a cation selective membrane. But as you can see in this particular one, we have a very graphene-like backbone with these very stable aromatic carbon-nitrogen hexagonal backbone with these negatively charged pores. And we show here that a model of a hydrated lithium ion is just the size to fit through one of these sulfonated pores and is highly attractive to these positively charged metal ions, whereas even sodium and potassium are slightly too large to get through there, even though their negative charges might attract them to the pore. And so next slide shows our synthetic routes, and we have multiple synthetic routes and multiple ways to both mess with the charged groups in the pores as well as the size of the pores. And so here you see that aromatic carbon-nitrogen backbone. In this particular pore, we have carboxylate groups, which are in neutral pH is not protonated as shown in the pore there. They will be negatively charged. And we see that triple bonded acetylene type group can make a spacer to make that pore smaller, or we could remove that spacer and put smaller groups there to enlarge the pore. And this is made from the precursors on the left with a very simple condensation reaction, highly utilized in lots of polymer prep, where the product is just water from the ketones condensing with the NH2 groups. In the next slide, we show an alternate chemistry where now we have sulfonate groups in the pores, and we're using this cyano group and NH2 condensation reaction to produce a slightly different sized pore with the sulfonate groups, and now a slightly larger one. But again, we could put CH2 groups between that sulfonate group and any number of them, or that carbon triple bonded group in there. So we can finely tune both the size and produce these highly negative charged pores to really make it selective for size and charge to only let lithium go through that pore. So the next slide shows how we are going to configure this membrane. And right away, if you were paying attention, you would say, yeah, well, there's only a few hundred parts per million of lithium in this brine. So how are you going to get any current density out of this membrane electrolysis cell? Well, the idea then is that you have to have a very high membrane area and a very high flux. And also you have to have a very low diffusion lengths. So we have begun to both envision and do calculations. This is mostly Jonathan Brandt, the engineer in the system, to design new membrane configurations that will have both high throughput and very, very small diffusion lengths, so that we can really get a total current density, a total amount of current in this membrane configuration, so that we can get basically high flux of lithium out of a very low concentration of lithium ions in the brine. And this proof of concept in this spherical wound configuration has been demonstrated for electrodialysis earlier on. And our lithium selective membrane would actually it'd be a simpler design than even that. And so phase 2, then we really have to develop this membrane configuration. And the next slide shows again some of the original calculations. So this shows that you do always have energy losses when you have an electrochemical cell. And so we can see the blue curve shows basically the limiting current that you could possibly expect. And then there's also energy from having to pump to get high fluxes and inefficient lithium transport and mixing. And it's from the, and you'll see you'll also get lithium depletion as you traverse this spiral membrane. So there will be a lot of modeling we'll do in phase 2 to see what the ideal configuration of this membrane flow system is. So we have to optimize the spacing between the electrodes and what lithium extraction efficiency. I mean, you're not going to go to 100%. You'll have to go to something like 90, 95%, just to the fact that, you know, it's diminishing return at a certain point. But we feel that we can get very highly purified lithium hydroxide directly from the brine, but also produce the added value of green hydrogen and perhaps pure oxygen and or chlorine, which are both valuable commodity chemicals. And so the last slide, I think, is just a pitch here that we also think that this technology, if we are allowed to further development in phase 2, would also be really highly advantageous to replace the evaporation technologies where, because they have solar energy available there, would also be using green energy to produce, again, valuable commodity chemicals plus lithium in one step, not over the many months process, where you're using solar energy rather inefficiently just to basically evaporate the brine selectively. And so in our case, we're basically getting a lithium ion for every electron we put into this system. Of course, it won't be 100% current density or current efficiency. There will be some resistive losses and such things, but those will all be worked out in our modeling. Plus, we do have this very, very precise control over the membranes, and so we'll be really doing 2 feedback loops at a time. One is it can always improving and testing the new chemical compositions. And again, like graphene, we can make these very, very thin because they're very, very strong. And we also know how to cross-link these membranes so that we can link these 2D materials from layer to layer by sacrificing some of the reactivity in the pores to then even make them still only nanometers thick, but very, very, very stable, like graphene. So we have very high fluxes. So again, that we can get very high fluxes of very thin.
Bruce, I hate to cut you off, but I want to make sure we have enough time for IAP feedback. Thank you so much for your presentation. Like I said, we'll go ahead and open up for some IAP questions. And maybe while the IAP is coming up with some questions, Bruce, I wanted to ask you for test 3, do you have any detail on how you would plan on testing your technology?
Well, I mean, John Brandt's lab has got some pretty good scale up. He's got a high bay thing there. Lithium and sodium. And so there's that feedback loop on the membranes, but in parallel, we'll be building up this kind of spiral configuration for our flow through membranes. And that has been somewhat scaled up in the electrodialysis. But so I think in phase 2, we will be at the point, hopefully, where we have a pilot scale membrane running that does lithium separation. I mean, small pilot scale. I'm talking more laboratory pilot, where on phase 3, I'd say the middle of phase 3, we might have an actual something that could work on the geothermal brines. Again, we have to have the pre-treatment because these ultra thin membranes will need to not have too much fouling and scaling in order to keep operating. Though the temperature problem is not a problem. These things are very, very stable, like graphene, up to even 400 degrees C in air in oxygen.
Thank you. Right, we have about a minute left. If there's any other questions from our IAP.
Have you estimated how much power, say from a 50 megawatt power station, how much of that 50 megawatts do you need for your electrolysis?
Sorry, it was a bit garbled. This
Say you have a 50 megawatt power station, how much of that electricity do you need for the electrolysis to remove the lithium?
Oh, well, we would, yeah, it would, I mean, again, it depends how much this is scaled. But again, I think our current, it's basically, you could figure it out. Even at 90% current density, we're getting a lithium separation for every electron. That's pretty energy efficient.
Yeah, fair enough.
And then we get one hydrogen for every 2 electrons, 1 H2, right? So, because you need 2 electrons there.
Great. Well, thank you, Bruce Parkinson team, or Bruce team, team of one. Thank you. All right, we'll go ahead and move on to our next presentation is from MIT again, Team Lithium from Home. Whenever you're ready to get started.
All right, you can go to the next slide. So we are Team Lithium from Home. You can go to the next slide again. So our team is composed of 3 PhD students and Professor John Lienhardt, our advisor, and 1 research affiliate, Dr. Kumar. Our team has a strong balance of industrial research experience with both computational and experimental backgrounds. And then our lab has a demonstrated history of entrepreneurship, including the first water company to achieve half unicorn status. You can go to the next slide. So we have a patent pending treatment train that includes all the processes you see below. So we have a pre-treatment step, selective separation, concentration and water recovery, and then crystallization. We're going to briefly discuss all of these pieces and have a special emphasis today on the selective separations part. So our design leverages the brine effluent from existing geothermal power plants at the Salton Sea in order to use the reduced temperatures coming out of the plant. Next slide. Next slide, please. So our phase 2 goals were to demonstrate lithium concentration and optimize our system for lithium selectivity. We're finished with those 2 steps, and we're going to, in the next month, finish modeling the last of our system processes and optimize that system to produce a detailed flow diagram, which would be the system that we're proposing to build in phase 3. Which would be our demonstration of that minimum viable product. And beyond that, we would scale the system to produce high purity lithium while meeting targets for cost, energy expense, and water consumption. So our pretreatment stage uses industry standard pretreatment processes to remove contaminants derived from iron, silica, zinc, manganese, and lead. The system is composed of 2 reactor clarifiers. In the first, we add in air and limestone. In the second, we add in lime. We remove iron hydroxide, andradite, and then metal oxides and hydroxides. And some of those are things that we might be able to valorize and have an additional revenue stream for this system. At that point, we add acid in to reduce the propensity for scaling and also to enhance the selectivity of our selective step. If you go to the next slide. So after pretreatment, we use a combination of water recovery and selective separation stages to produce a lithium-rich brine. So in the selective stage, we've been considering selective electrodialysis and nanofiltration to separate lithium from the divalent or multivalent ions, which are the key contaminant that we're concerned about after the pretreatment step. And so we've been able to show nanofiltration with a high selectivity at a low pH of around 10. We'll discuss that more in just a second. But if you go to the next slide, our selective step does need to be, we do have to add water in to dilute the system down to increase the recovery and the performance of the system. However, we're able to recover much of that water back using forward osmosis. The forward osmosis system we've proposed can operate at a recovery ratio of around 30 to 50%. And this really helps to reduce the the dependence on external water supplies and to reduce the amount of water added into the system. Next slide. So in order to concentrate what's coming out of that forward osmosis system, we've looked at a number of different technologies, including osmotically assisted reverse osmosis, low salt rejection reverse osmosis, and those are membrane brine concentration steps. That would probably be a longer term solution. For phase 3, we'd probably propose a thermal brine concentration using the on-site excess thermal energy, just as that's a more mature technology for demonstration, with long-term plans to go to membrane brine concentration. What comes out of the brine concentration step will go into a mixed suspension, mixed product removal crystallizer, which will produce high purity lithium carbonate, which would be our final product that we're planning to have at this time. So you go to the next slide. Yep. So we have a bench scale nanofiltration setup, as well as a bench scale monovalent selective electrodialysis setup that we've been testing in the lab. We've been testing synthetic salton sea brines that include lithium, sodium, potassium, calcium, chlorine, and sulfates. We've been testing these brines over a range of concentrations, pressures, and pHs to understand the selectivity of the membranes that we've looked at. And so we use ICP OES and gravimetry to understand the fluxes of water and the relative fluxes of different ions in the system. Next slide. So a few different things to talk about here. So if you'll direct your attention to the left graph first. So what we're showing here is that at the key metric we're looking at is the separation factor, which is a measure of lithium recovered relative to the divalent ions, in this case calcium, on a percentage basis. So conventionally people have operated at neutral conditions, where the polyamide selective layer takes on a negative surface charge. And what we've been able to show is that by reducing the pH below the isoelectric point of the membrane, we're able to functionally charge the membrane or flip it to a positively charged surface rather than a negatively charged surface. This helps to repel the more strongly charged divalent ions and allow the monovalent ions, especially the lithium, to pass through the membrane, which allows us to achieve this high separation factor that you see in the orange bars on the left graph. And so the key result here, which you'll see on the right graph, is that we've been able to increase the separation factor to this, essentially this dotted line, which is kind of the trade-off that we see at the cutting edge of membrane research for separation factor versus water permeance. And we've been able to increase that separation factor by nearly an order of magnitude while maintaining a high water permeance. And this is for a low-cost, off-the-shelf membrane. So our value proposition is based on four different key points that we're evaluating on. The cost of lithium is obviously one, water consumption, energy consumption, and then purity and yield. And if you go to the next slide, what we've been able to show is that we think we can produce lithium at competitive water and energy consumption targets while maintaining exceptionally high purity and relatively high yield. And again, this is all with the key components that are commercially available and off the shelf. And so our next steps are to continue to optimize our existing system design, and with a special emphasis on the crystallization part is kind of the last piece that we're kind of nailing down now. Moving forward, we're going to work on scaling this up to pilot scale and then testing some additional membranes. The membranes that we've considered at this point do not operate at high temperature, but these high temperature membranes that we would potentially use are available for purchase, and so we will work towards testing those. In terms of ways that the IAP can help us, we've been in some business and customer discussions now, but discussing and better understanding with geothermal operators exactly what is coming out of the geothermal plants is an area where we still have a few questions. And then also understanding how excess thermal energy might be able to come from the geothermal plants to our system. And then finally, We know there's a challenging IP and regulatory landscape. Dan Hoyer, our current IAP member, has been very helpful in helping us to understand some of the challenges there. But further understanding that will be one of the issues that we have going forward. And I think that wraps up our presentation, and we're ready for Q&A.
Thank you so much. All right, we'll go ahead and open it up to our IAP members. While we're waiting on our IAP members for questions, a question for you is, how does your solution improve on environmental impacts of direct lithium extraction?
Yeah, so that's a great question. You guys can jump if you have more stuff to say, but we've been, our design is able to, we're still optimizing everything right now, but we think we'll be able to reduce the water and energy consumption compared to existing solutions. And then in terms of other challenges, like we will have some chemical use in terms of acids and bases and things like that. But those are something that we may be able to produce on site to reduce the environmental impact of that. And then there will be some small amount of waste streams coming from our pretreatment process. But some of those, again, as we mentioned, might be waste streams that we can turn into revenue streams and create use out of those. And the other streams we have been able to keep to a bare minimum. Yeah.
Thank you.
Oh, yeah, that was in an appendix slide. You can jump past that.
So you mentioned oh, I'm sorry, was there an IAP member asking a question?
It's Mike O'Sullivan here. Just
Go ahead, Mike.
How much extra water do you require to dilute the brine?
If you can back up a slide, or sorry, one more slide. Yeah, so I don't have that number in terms of the per like unit of brine, but we have this per ton of lithium carbonate equivalent. I don't know if you guys know that number off the top of your head. Yeah, I don't know that. I don't know what this conversion is in terms of like water per unit of brine. But yeah, we should. I mean, we can back calculate that from this. The approximately or just under a 1 acre foot per ton of lithium carbonate equivalent.
Yeah, thanks.
And I believe, yeah, this 0.75 acre feet per ton is at 85% yield, I believe. Yes.
The question I was going to ask you, or mention that you were going to start using different high temperature membranes. Can you walk us through some of the metrics that you will be using to get to a membrane that works your Goldilocks membrane?
Yeah, so and that will be a challenge of balancing the temperature of the stream without having to do additional cooling from what's coming out of the geothermal plant with the temperature capacity of the nanofiltration membranes that we use. And so we were just using off the shelf membranes at this point for testing. But we know that the higher temperature membranes exist. And it's just a matter of, at this point, running the same test that we've run now to understand how the separation factor of those membranes operate for our treatment process. But yeah, obviously, if we could have the same membrane that we have now, just that would operate at higher temperatures, that would be great. And we'll have to evaluate based on the capital costs and then the trade-off there with the amount of cooling that may need to be done.
Great, thank you.
Thank
All
you.
right, we have about a minute left, a minute and a half left. Are there any other questions for our IAP members or from our IAP members? All right, there's nothing else. I think this is our last participant for today. We'll go ahead and turn it over to Rice University with Leseed. Am I close on that?
Yes.
Perfect, great.
Thank you.
Whenever you're ready.
So our team is called LISID and stands for lithium selective electrodialysis. Next slide, please. So the biggest challenge in direct extraction of lithium is the need to produce a clean solution with high lithium concentration, but very low concentration of other cations. Can you go back to the previous slide? Thank you. And this requires separation between lithium and other and divalent cations, as well as other monovalent cations, which are usually present at concentrations much higher than lithium in the geothermal brine. So our team's approach, which I'll explain in more details later, is based on the development of a lithium selective cation exchange membrane and a novel process design to directly extract and concentrate lithium from a pre-treated geothermal brine. Next, please. Our team consists of 5 members from Rice University. My name is Qilin Li. I'm a professor in the Department of Civil and Environmental Engineering, also the Associate Director for Research for the NSF-funded Engineering Research Center for Nanotechnology Enabled Water Treatment. I'm also the founder and president of a startup company that focuses on the treatment of hypersaline wastewater streams. Working with me are Dr. Ibrahim Abdallah. He has a PhD in chemical engineering and is a research engineer for our new center and is in charge of our mobile wastewater treatment testbed systems. Dr. Kui-Chan Zhou, a postdoctoral associate, also worked for our new center and just recently started a faculty position. And 2 PhD students in my lab, Xiaochuan Huang and Yuren Feng. Among the 5 of us, we have a lot of experience designing and constructing and testing water and wastewater treatment systems from bench scale all the way to pilot scale. Next, please. So in our proposed method, the geothermal brine after power generation will first be pre-treated to remove interfering species, especially membrane foulants such as silica and iron. And we're working with a company that specializes in treatment of high salinity oil and gas produced water and has a lot of experience in pre-treating water that's similar to the geothermal brine, although with probably lower dissolved silica concentration. And their process can handle high temperature streams. The pre-treated geothermal brine is then processed by a novel 2-stage electrodialysis system. That's the core component of our lithium extraction process. Our first stage electrodialysis utilizes a novel composite cation exchange membrane with super high perm selectivity for monovalent cations over divalent cations, which allow us to produce a concentrated lithium brine almost completely free of divalent cations. In addition, we use a tailored aqueous solution as a carrier stream on the concentrate side for lithium to minimize the transport of other monovalent cations so that most of the electrical energy consumption is used to transport lithium instead of sodium or potassium. And the first stage, not yet, please. The first stage electrodialysis reactor will produce a clean lithium containing brine free of divalent cations, which will increase the concentration compared to the feed stream. And this clean brine is then sent to the second stage electrodialysis reactor to produce the final concentrated lithium brine which will be used to produce lithium carbonate or lithium hydroxide using chemical precipitation methods. Next, please. So to ensure this process works at high efficiency, we have two major project goals for this phase of the competition. Our first goal is to develop a scalable fabrication method for the high lithium selectivity cation exchange membrane. I'll show you some preliminary results on my next slide. And we aim for this membrane to achieve more than 90% removal of divalent cations, even at large scale without any chemical addition. And we wanted the fabrication method to be such that the cost of the selective cation exchange membrane is comparable or similar to existing cation exchange membranes. Our second goal is to test and optimize the process design in order to maximize the charge efficiency for lithium transport, as well as the recovery and concentration of the lithium in the final clean lithium brine. Our current performance goal is set to reach at least 10x lithium concentration in phase 2 and more than 60% charge efficiency for lithium transport in the two-stage ED process and greater than 95% lithium recovery in the overall process. Next, please. So in the lab, we have successfully fabricated a monovalent selective cation exchange membrane and tested it in a small bench scale electrodialysis reactor. So here, the feed water we use is much simpler and has a much lower salt concentration and geothermal brine. And we recognize the difference between our test water and the real geothermal brine. And this is our next step of the goal of our next step experiments is to test solutions or feed water that's closer to the geothermal brine. But you can see in this simple proof of concept experiment, we were able to demonstrate complete removal of divalent cation. So here you see a small green bar here. We put it there. It's actually 0 divalent cation flux, but we just put some number there to show you we have a data point. We have 0 divalent cation transport across the membrane, but fairly high lithium flux. And because of the use of our tailored extractant solution on the concentrate side, we were able to also minimize the transport of sodium as well, even though the membrane itself is not selective between sodium and lithium. And we were able to make this membrane using commercially available materials and show that the electrical conductivity and other properties of the membrane, including cation anion selectivity, very similar to existing commercial cation exchange membranes. Next, please. So our anticipated performance goal for this phase of the study is that we will be able to reach a lithium flux of 20 mole per meter square per hour under typical electrodialysis operating conditions. I wanted to mention that in our preliminary experiment, we used a very low current density of 20 milliamps per centimeter square, which is 2 orders of magnitude lower. So we anticipate that with a typical electrodialysis current density, we will be able to reach a lithium flux at 20 mole per meter square. And given this flux, as well as our current flow rates used in the preliminary experiment, we calculated that our energy consumption to produce a clean lithium brine at 4,000 ppm would be about 15 kilowatt hour per cubic meter of this concentrated lithium brine. Next, please. So our value proposition is the following. We will replace the evaporation, lime and soda, precipitation of calcium and magnesium, and boron extraction steps in the current lithium mining process with the 2-stage lithium selective electrodialysis process. Next, please. And the elimination of the evaporation step will drastically reduce the footprint of the lithium extraction system from hectares to meters square, a reduction of several orders of magnitude. It will also greatly reduce the production time as we can process more than 2.4 cubic meter geothermal brine per meter square of the membrane per hour. Furthermore, this avoids the negative environmental impact of evaporation ponds, which also leads to a very large loss of water. Our process is essentially a zero water consumption process. By eliminating the chemical precipitation step for calcium magnesium removal, we can reduce the chemical use by more than 80% according to our chemical reaction equilibrium calculation. This also leads to a large reaction in the chemical sludge production of more than 450 kilogram for every cubic meter of the brine processed. And most importantly, the lower chemical use as well as the associated transportation and storage cost is anticipated to reduce the overall lithium production cost by more than 30%. Next, please. So in summary, we proposed a novel two-stage lithium selective electrodialysis process that can produce a clean lithium enriched brine with high lithium concentration, high recovery, and high purity. And this will be achieved by the development of a composite cation exchange membrane with extremely high selectivity for monovalent cation versus divalent cation, as well as the use of a tailored aqueous extractant solution, which minimizes the transport of other monovalent cations and therefore maximize the charge efficiency for lithium transports. And finally, a novel process design that recirculate the streams in different ways to maximize lithium concentration, recovery, and purity. So far, not yet. In this phase, we have successfully fabricated and demonstrated the performance of the composite cation exchange membrane with very high selectivity. We also demonstrated the effectiveness of the aqueous extractant solution, which greatly enhanced lithium transport charge efficiency. And more importantly, we developed this novel two-stage electrodialysis process that maximizes lithium concentration. Our plan for the next phase is to design and build a mobile prototype that can process the brine at about 0.5 liter per minute flow rate, which will generate a lithium enriched brine for 0.7 to 1.5 kilogram of lithium carbonate per day. And this will be an integrated system with necessary pretreatment processes and will be tested at either a geothermal power plant, or if we can get a more realistic feed water, we can do offsite testing as well. Next, please.
I hate to interrupt, I apologize, but we're over time here and I want to make sure
Only,
that the IAP
yeah,
has time to provide some feedback.
Yes, so those are some of the support we are hoping that could help our next phase of the study. We're looking for manufacturing partners that can help us scale up the production of the selective membrane. We're also looking for a way to get some real water samples for laboratory testing before we go to field demonstration, and finally, of course, connection to a potential testing site for phase 3.
Thank you.
Thank you.
IAP, would you like to ask some questions and provide feedback? So you mentioned briefly about environmental energy savings, but beyond the energy savings, are the other environmental impacts that your technology could address as opposed to the current state of direct lithium extraction?
Yeah, so some of the common benefits that I think many other teams methods also could achieve would be reduction in chemical use and a reduction in chemical sludge production, because chemical sludge will have to be disposed of afterwards. And also it's essentially a zero water consumption process. So we don't really, we need a very minimum amount of fresh water to get the system started. And the rest will just use the water in the brine.
Great, fantastic.
And electrodialysis is also a process that can be powered directly by solar energy. So if we can set up with a solar panel system, and you can also potentially power the whole system by solar energy.
Great. Thank you. Thank you very much. Thank you for your presentation today. We're just about at time. So I want to go ahead, and I think you are our last team for today. Yeah. All right. Well, thank you again for your presentation, and thank you to everybody who presented today. That was quite a marathon of presentations, and you all did fantastic. And I thank you so much for your time and participation today. I want to remind everybody to again check the chat box for any questions or helpful pointers from your other fellow teams, competing teams. And I want to thank again our IAP members that provided some great questions and feedback today to everybody. And so today we're wrapping up day 1 of our innovation pitches, and we will continue for day 2 on Thursday, March 31st, same time, same place. So I hope that you can all join us then to either listen in or hear your pitches. So thank you again to everyone for participating today, and I will see you for day 2. Thank you. Bye-bye.
Thank you.